John Milnor is so important, he requires 2 introductions. So let me just say briefly that the conference is in honor of Dusa McDuff's birthday. I'll be tactful and not say which one. She was born in England, but actually was brought up in Edinburgh. But for the last 40 years, she's lived in the United States and worked there. And about 40 years ago, she married Jack Milnor. And so, I mean, the natural comparison which both Michael Atiyah and I made, that to mathematics what Bill and Hillary Clinton are to politics. At this point, I will, without going into any details, we will now I'll hand over to Sir Michael Atiyah, who is almost a contemporary of John Milnor's, and he will talk. He'll introduce the actual speaker.
Well, thank you, Andrew. As usual, this was sprung as a surprise on me the last minute. Would you mind introducing John Milnor? Well, I couldn't refuse, of course, but I come unprepared. Got no speech is prepared. But I thought I'd say a few words. First, with the audience here, I don't think I need to say much. He's obviously sufficiently famous to attract so many people. He's been around in the mathematical world for quite a long time, and he's proved marvelous results and had many awards. His title, his lecture's up there, but I first met, he's called Jack to all his friends, John to some people. I never worked out why John is abbreviated to Jack. They're both 4-letter words. It's not quite clear to me what gain you make, but it becomes some kind of a please, you have to shorten your name from John to Jack. Oh, there it is.
Must be the French, Jacques.
Yeah, I thought of that, but there's Jean-Jacques, you see. Yes. So, anyway, Jack, as we know him, I met him many years ago. Now, looking around the audience, I think possible, except I think I'm possibly the oldest person here. I'm not quite sure, because not everybody has their age on their lapel, and Jack is just a little bit younger than me. Anyway, I met him when I first went to Princeton as a postdoc, sometime in the middle of the last century. Give or take 10 years ago. I think it was 1956. And I remember clearly being in this lecture room, and I've forgotten what it was about. Some young chap at the back asked a question. I said, "Who was that guy?" "Oh, that's a very bright student, no? Very brilliant." So I met him, and I was told he was the up-and-rising young student in Princeton at the time. That's 1956. Well, you can probably guess roughly what generation we are by working backwards if your sums are good enough. And I've kept up with him ever since. We've been it's in the same institution sometimes, and if not, other places. And of course, I met Dusa in other directions. So we've got quite a lot in common, and our mathematics has overlapped. And he's a marvelous, not only a mathematician, but a marvelous expositor. And this is his chance to show his powers of exposition. He's going to talk to an audience that's supposed to know nothing at all and tell them about some very important stuff. And I'm sure you'll all enjoy it. And at the end of the time, when you want to ask difficult questions, I'll hand you back to Andrew, who is in charge of the difficult questions. Now I can lie back and enjoy the talk like all of you. John, Jack.
Well, thank you for that introduction. It's always a little embarrassing to give a lecture when the introducer knows more about the subject than the speaker, but at least he'll be here to, in case I make mistakes, to point them out. Let's see, I should get this thing turned on. Oh, there it is. Okay. Well, I'm talking about a subject which has been studied intensively for more than 300 years. So it's, I think nobody, even Sir Michael, not everybody knows everything about it, but there's a lot to learn. So I'll start roughly 300 years ago with Isaac Newton, who was the, as far as I know, the first person to make an intensive study of cubic curves. Here are a couple of diagrams, from his work on cubic curves. So you can see from the diagram, for example, that a cubic curve may have two different components. Let's see, how does this? So this is an example of a cubic curve with two different components. This is an example with the singularity, a self-crossing or double point. Well, I should start by saying what I mean by a cubic curve in this context. So I consider the plane, the Euclidean plane with coordinates x and y, and all the points satisfying a cubic equation like this, where at least one of the third degree coefficients is non-zero, so it's not just a quadratic equation. So anything like this is called a cubic curve. Notice there are an awful lot of coefficients here, which you can change any one of them. So what this means is that there are an enormous number of distinct cubic curves. It's a very large and wild family. So here's a typical random, in quotes, cubic curve. You can see that it doesn't seem to have any obvious symmetry. Now, maybe the most basic and important fact about a cubic curve is this. Suppose that you intersect it with a straight line. Then there are at most 3 intersection points. And that's quite easy to prove. If you intersect it with the line, then you have a single coordinate along the line. It must satisfy a cubic polynomial equation. And it's a basic fact of algebra that a cubic polynomial equation cannot have more than 3 solutions, except in one special case if it's identically 0. So this is only true if we rule out the case where there's an entire curve of points contained in C. And notice that so far my definition is very general, so there's nothing to rule that out. Well, so let me start with this basic fact and take a look at Newton's example. So here is his example of a cubic curve, and if we draw a line through here, we see that there's a double intersection there, a double intersection there, a single intersection there. There's 5 intersection points. So he was a little careless in drinking his diagram. He didn't have, clearly it wasn't that easy to make good diagrams in those days, but, the cubic curves do look very much like his picture. It's just that he doesn't have it quite right. I think what he was trying to draw is something more like this, where if you draw a line, it does only have 3 intersection points. Here, this one. Let's see, how do I do this? Here, this I'm counting as a double intersection point and a single one, so there's a total of 3. Well, the next person after Newton to study cubic curves was Colin Maclaurin. And he carried Newton's work further. I'm afraid I'm not really familiar with much of what he did, but I did find one simple example of a theorem that he proved that's illustrative of the kind of thing I want to talk about. So we suppose we start with any cubic curve and draw a straight line which intersects it in 3 points. And then he constructed the tangent to the curve at each of these points. So this gives us 3 tangent lines to the cubic curve, and each of these tangent lines intersects the curve in a 3rd point, or at a 2nd point, or if you count the tangent intersection as being a double point, it's a 3rd point. And the theorem states that the points you get in this way all lie in a straight line. So this is clearly condition that won't be satisfied for just any curve. It's a tight restriction on cubic curves. And I hope to explain why it's true later, but let me just take it as an indication of the kind of thing that was known more than that far back. So what did I say? That was 1740, so yeah, so it's about 270 years ago. Well, the subject has been studied intensively ever since. Many famous mathematicians have contributed. There was D'Alembert in France, Euler in Russia, Legendre in France, Abel in Norway, Jacobi in Germany, Hesse in Germany, Weierstrass in Germany, Mordell in England, André Weil in France. The list could go on and on. There's an enormous amount that one can say about curves, and clearly I can only say a small amount. So the first thing I want to do is to recalibrate slightly. I defined cubic curves in the Euclidean plane, but that's really the wrong place to look. We should be looking in the projective plane. The theory is simpler and makes more sense if we do that. So I have to explain what the projective plane is. Well, the theory of projective geometry perhaps was inspired by Italian painters in the Renaissance who wanted to have an understanding of perspective. I think the Brunelleschi was the pioneer in this, and here's a typical example of a painting by Perugino, which illustrates the principles of perspective, giving a feeling of depth in a painting by considering lines which seem to converge, which on the canvas converge, but to your eye look as if they're parallel. Or here's a more homely illustration of this, a highway in Finland. And you can see that the edges of the road seem to converge to a point. So what does it mean to say that parallel lines meet at infinity? It's certainly not true in Euclidean geometry. In Euclidean geometry, parallel lines never meet, but there is a kind of geometry where it makes sense, and that's what I want to talk about. Well, this is a simple device. It's been known probably for 2,000 years, which helps to illustrate this. So a camera obscura is a darkened room with a small hole in one wall. So if you take a bright object outside, like this tree, it gets projected on the opposite wall, turned upside down. And we can represent this situation. Oh, here's a different illustration of in this case, there are two rooms, one light and one dark, and the wall in between them has a small hole in it. And then the picture on the wall, bright wall, gets projected and turned upside down onto the wall of the dark room. In this situation, we can model mathematically by taking two planes in Euclidean space and one point, which is labeled 0, 0, 0 here, which represents the hole in the wall, or the pinhole. And then if we take any point in the left-hand plane and draw a straight line through it in the pinhole, it will usually hit the right-hand plane. And in this case, we say there's a transformation from the left plane to the right plane, which takes the point x, y, z in the left plane to the point x prime, y prime, z prime in the right-hand plane. And this transformation has the property that it maps lines to lines, but it's not a perfect transformation. There are points on the left which don't have any corresponding point on the right. This has the effect that parallel lines on the left often map to lines which cross each other on the right. Or vice versa, you can go backwards. Well, to make more sense of this, mathematicians over the next few hundred years learned to introduce the concept of the projective space, or projective plane in this case. And the simplest definition is that projective plane, the real projective plane, is just the set of all lines through the origin in the three-dimensional Euclidean space. And, well, what does it mean for 3 points to be on a line through the origin? It means that the vector x, y, z multiplied by some non-zero constant is equal to the vector x prime, y prime, z prime. That's just an algebraic way of writing down the geometric statement. And the notation one uses this: x colon y comma colon z is the represents the ratio of x to y to z, and think of this as a point in the projective plane. Or another way of thinking about it is to notice that every line through the origin intersects the unit sphere in two antipodal points. So we can think of the real projective plane as just something an abstract mathematical object that we obtain from a unit sphere by identifying opposite points. So let's see. So this point on one side is to be identified with this point, which you couldn't really see. It's on the opposite side of the sphere, but if you could see through the sphere, that's where it would be. Well, to illustrate why this is useful, here's a classical example. So instead of looking at cubic curves, suppose we look at quadratic curves. So here's an example of a quadratic equation, x squared plus y squared equals z squared, which defines a cone of straight lines through the origin in 3 space. So we can think of this as describing a circle in the projective plane. And in fact, if we intersect this, sorry, I have to point this way. If we intersect this sphere with a horizontal plane like this, we get a circle. But we could also intersect it with a vertical plane. In that case, we'd get something quite different. So in fact, by varying the plane that we intersect it with, we can get a parabola, a circle, an ellipse, or a hyperbola. So we just have one curve in the real projective plane, but by intersecting it with different planes, we can get a great variety of different quadratic curves. This, of course, was known more than 2,000 years ago. Now, for cubic curves, there are many more cubic curves, so of course there are many more possibilities, but it becomes even more important to simplify the situation by working in the projective plane, where somehow everything that you need to know is already there. You don't have to look at extra points at infinity. Well, okay, what are the cubic curves I want to talk about? I gave a quite general definition before, and it's easy to extend that to the curves in the projective plane. But I always want to assume that our curves are smooth and irreducible. So smoothness means that the partial derivatives are never both zero, or in terms of a picture, it means that there's no self-intersection. This is an example of a equation of a curve which does have a self-intersection, so that will be ruled out. It can't have a cusp point. And I also want the curve to be irreducible. That means that the curve doesn't contain any line. This is an example of a cubic equation defining a curve which splits into 2 parts, a circle and a line. And it's not singular anywhere in the real plane, but this also will mess up our argument, so this is not allowed. Okay, now with this introduction, I can go back almost 2,000 years again and introduce another important concept, which goes back to Diophantus, if we start with any cubic curve and take 2 points on it, we can draw a straight line through them. And this map, which takes the pair PQ to the point R, is called the chord-tangent map. You take the chord through P and Q and extend it and see where you end up. And I'll use the notation P star Q for R. So P star Q means the object you get by drawing a line through P and Q and following it till you hit the curve again. But notice this is a completely symmetric relation between P, Q, and R, so we could just as well say that Q star P is R, or that P star R is Q, or that Q star R is equal to P. It's just a shorthand way of indicating that the 3 points lie on a line. But the marvelous fact is that it extends to this correspondence easily makes sense in the limit even as the points P and Q come together. In fact, you get a infinitely differentiable map this way, or continuous, actually real analytic. And now how does this work? Suppose example that Q moves closer to P, so that we, let's see, move the point Q closer to P, then the point R will move up. And we get this situation when P equals Q, then the chord running them turns into a tangent. That's why it's called the chord-tangent map. And we follow this tangent till we get another point, as in the Maclaurin construction I was describing earlier. In that case, we say that P star P is equal to R. But this is, again, a relationship between the double intersection P on one side and a single intersection on the right, so we could just as well write this as P star R equals P. And we can be even more degenerate. Suppose we move P and Q to the right, then R will move down, and at some point they will come together, and we'll have a line where the tangent doesn't have any other intersection. This now has a single triple intersection there, and we state that P star P is equal to P. These points with this property are called inflection points or flex points. They play a very special role because they're the unique points which are somehow picked out by the local geometry, different from all other points. Well, closely related to this is a different structure on the curve. I've used this operation P star Q, which is algebraically a very strange object. It defines a symmetric object between the 3 points, but we're much more used to an operation like addition, which you're given 2 numbers, you can add them and get a third number, and similarly, given 2 points on a cubic curve, you can add them to get a third point. You need to make one choice before you can do this. You have to choose a base point, and the construction will be much easier to describe if we choose a flex point as our base point. So suppose we take a cubic curve and pick out one flex point and call it O. Then the claim is there's one and only one commutative and associative sum operation making the curve into an additive and abelian group which satisfies just 2 conditions. The first is that O is the 0 element, so if you take any point and add O, you get P. And the second condition is that 3 points are collinear if and only if their sum is O. Well, so what have we got to work with here? I want to prove that there's one and only one operation satisfying these conditions. So proof of uniqueness, suppose we have such an operation with O as identity element and that 3 collinear points have sum 0. Then given P and Q, I said I first take the star product P and Q, the chord-tangent map, and then star that with the base point. So here's a picture of that. So starting with 2 points P and Q, we first follow a straight line through them until it hits the curve again. And then we take that point R and draw a straight line to the base point and continue it until we hit the curve again. Then PQ and R are on a line, so P plus Q plus R is equal to O, or think of it as 0. And S, 0, and R are on a line, so S plus 0 plus R is 0. And just combining these two equations, you see that P plus Q is S. So this shows that there can only be one operation satisfying these conditions. P plus Q must be equal to S. And now to prove it exists, we just go backwards and use this construction to define P plus Q. So it's the same picture, but just labeled slightly differently. Given P and Q, you form P star Q, join it to 0, and call the endpoint P plus Q. Now it's very easy to check that this is very easy to check that this is satisfies the first condition, that O is a 0 element for this sum. And it's easy to check the second condition, that if 3 points are collinear, then their sum is 0. It's also easy to check that it's commutative. P star Q is the same as Q star P. So all we need to finish the argument is to prove the associative law. Unfortunately, this is not so easy to prove, so I won't try. But you can find it in any textbook on elliptic curves. One beautiful example of a textbook is a book by Castle's Lectures on Cubic Curves, or there's Serge Lang's book on elliptic curves. In any case, this is a true statement, and I will assume that it's known. Well, I used the chord-tangent map to define the sum operation, but it's sort of trivial to go backwards. If you know the sum operation, then it's easy to define the chord-tangent maps. Because suppose you have 3 collinear points, so that P plus Q plus R is the 0 element. Then P star Q is equal to R. But just from arithmetic, from this equation, P plus Q plus R equals 0, we can write R as minus P minus Q. So this proves that we can compute the chord-tangent map in terms of the sum operation. In particular, P star P is minus 2P, where minus 2P means we add P to itself and then take the negative. Well, one correlate this, now we can prove Maclaurin's theorem. So suppose we take any cubic curve, draw a straight line through, which intersects it in 3 points, and then we form this chord-tangent map at each of these tangent points. So let's see, suppose, for example, this is P1, and this will be minus 2P1. This is if this is P2, this will be minus 2P2, and so on. And then, just from ordinary arithmetic, we see that minus 2P1 plus minus 2P2 plus minus 2P3 is the 0 element. And that is the proof. Well, the focus of this talk is on, to begin with, on real curves and later on complex curves. But actually, this chord-tangent map works much more generally. For example, I said that it's due to Diophantus, but Diophantus would not have been very comfortable with real numbers. The Greeks knew that there were irrational numbers, but they didn't quite know what to make of them. So he was interested in only rational numbers. So he was considering a cubic equation, say with integer coefficients, and asking whether it had a rational solution in fractions of integers. And the most literature on elliptic curves works over the complex numbers. This is the easiest case, the classical case, and the one with the most useful structure. Mordell in the 20s, so almost 100 years ago, proved a result which was very important to number theorists. Suppose you have an elliptic curve over the rational numbers, that is, you have a cubic equation with rational coefficients, and you're only interested in solutions which are rational numbers. Well, it was known that in some cases there were infinitely many solutions, and it seemed very hard to know how to deal with this. Well, Diophantus already used this as this idea that if you're given one solution, you can use the tangent map to find another, and you can iterate this procedure and get many other solutions. But what Mordell proves was that the group we get by this construction is finitely generated. So you can find if you can find a finite number of solutions, that all of the others can be obtained from the sum operation or from the chord-tangent operation applied over and over again. And now we switch to applied mathematics. The elliptic curves have a very important application these days because they're used in constructing codes which are important in everyday life. When you go to a cash machine to take out money, or if you send a message on a mobile phone, a message may well be encrypted, or the PIN that you enter in the cash machine certainly is encrypted so that nobody else will know what it is, and the ciphers that are used are often based on elliptic curves. Well, what cryptographers would typically be interested in is an elliptic curve defined over a finite field. For example, the integers modulo p, where p is a prime number, perhaps with 10 or 20 digits. Such things were very hard to find 50 years ago, but using computers it becomes quite trivial to find them. And in this case, we still have this group structure. So C is a group. The curve C is a group. In this case, it's a very large group, but finite. And it's easy to compute the sum operations. I put easy in quotations because I don't mean that I could sit down with a pencil and paper and figure out what the sum of two numbers is, the sum of 2 points on an elliptic curve is, but for a computer it's very easy. But the opposite operation, here by nx, I mean you take a point x on the elliptic curve and an integer n and add x to itself n times. And then you just have to perform the sum operation n times and you find out what y. Again, it's easy for a computer. But now what the cryptographer wants to do is to pick out some x, and you provide an n and say you enter the number n as your PIN in a cash machine, and the machine will then send out y to a central computer, which will check that it's the right number. And if somebody manages to hack the message and find out what y is, it's very hard to figure out what x was. Well, that was an aside talking about other uses of elliptic curves, but now let me go back to the real case and look at flex points. Well, remember that P is a flex point if and only if the tangent line at P has no other intersection with the curve, written as P star P equals P. And it follows that using the sum operation that p plus p plus p is the zero element. This shows that the set of flex points forms a subgroup of C consisting of all elements of order 3 together with a zero element. Well, as one corollary, the line through any two flex points intersects the curve in the third flex point, because if you have 2 points of a group and add them, then the negative of the sum is again in the group. So here you take a typical curve, and let me mark the flex points, drawing the lines, tangent line through each so that you can see the curve crosses its tangent line. That's the indication of a flex point, and these necessarily lie on a straight line. And we can sharpen this. For a real curve, there are exactly 3 flex points. And you could prove this by an elementary argument, but let me just throw in some heavier machinery. We know that the curve forms a nice additive group with a smooth group structure. And the curve, in some cases, the curve is topologically a circle, and in the other cases, it's topologically 2 circles. But in either case, there's a unique way of finding out what the sum operation is. The only such thing, groups with a smooth sum operation or some smooth product operation are called Lie groups, and the only Lie group structure in the circle is the standard one. And if there are 2 components, you just have the standard circle group and the direct sum with a group of 2 elements. And in either case, there's a unique subgroup of order 3. So this proves that every smooth, irreducible real curve has exactly 3 flex points. First of all, it is a theorem that every smooth cubic curve has at least 1 flex point. I don't know who proved it first, but it certainly follows from standard things in the literature. The second point is that you can actually define a group structure even when there's no flex point. It's just a little more complicated to explain, and I didn't want to confuse things. But that is a valid point. Okay, let me just go back to the general notion of projective geometry as it applies to situations. If we take a linear map from Euclidean space to itself, that means we just take a non-singular 3x3 matrix and use it to transform any line through the origin to a different line through the origin. Then it will map the projective plane to itself. That's called a projective automorphism. It just means we're taking a linear change of coordinates. And 2 curves are called projectively equivalent if there's a projective automorphism carrying one to the other. In other words, if each curve is, the first curve, say, is defined by some cubic equation, and we just use a linear change of coordinates, we'll get a different cubic curve, which is called projectively equivalent. Okay, I need this, and now I want to emphasize one particular point of view in projective, in study of cubic curves due to Hesse, who introduced a very simple normal form for cubic curves. There's a parameter k. In his case, it would have been a complex k, but for now, I want to take a real k, and you look at all curves satisfying, in projective space, satisfying this equation, which is homogeneous of degree 3, and therefore defines a family of lines through the origin, or a curve in the projective plane. And using this normal form, we can state the following classification theorem. Every smooth, irreducible real cubic curve is projectively equivalent over the real numbers to one and only one curve in this Hesse normal form. So in other words, the real number k is an invariant and is a complete invariant. And any k different from 1 can occur. In other words, if we take any k different from 1, then the curve defined in this way is smooth and irreducible. On the other hand, if we take k equals 1, the curve is not smooth and not irreducible. So this gives us a very simple overview of all possible cubic curves. Now, I'm a little embarrassed at this point because this is not a particularly difficult theorem. It could have been easily have been proved any time in the last 100 years, but we haven't been able to find any reference to it in the literature. Now, this is an enormous literature, and this is maybe more saying something about our lack of searchability rather than, but it seems likely that this was known, but we haven't found any reference to it. This note I'm talking about was just an attempt to give elementary proofs for some basic results, and this result sort of dropped out of more or less known things. But as I said, we haven't been able to find any reference. Now, the corresponding statement over the complex numbers is not true in that precise same form. It's rather certainly known, probably since the time of Hesse, or certainly for the 19th century, but during the 19th century. But a generic smooth complex curve, if we work over the complex numbers, it has 12 different representations in Hesse normal form. So it's much more complicated. It's only over the real numbers that this 12 drops down to 1. Well, one place, for example, where this is explained is a paper by Ardavani and Dogachev a few years ago, which is also a good general reference for the kinds of things I'm talking about. Well, I talked about the now I want to talk about the automorphism group. So we've talked about projective automorphisms of the projective plane, and if we look at projective automorphisms which take a curve onto itself, then they form a group. And an easy corollary to the classification theorem is that for any smooth irreducible curve over the real numbers, there are exactly 6 automorphisms. They form a group with 6 elements. This can just be identified with the group of all permutations of the flex points. So in other words, if you take the flex points and interchange them in any way, that extends uniquely to an automorphism of the whole projective plane, which takes the curve to itself. And these, if we take the Hesse normal form, then these 3 automorphisms are very visible. They're just a group of permutations of the 3 coordinates. And now, to prove this theorem, well, looking at the Hesse curve, since every curve can be reduced to the Hesse normal form, it follows that it always has a group of 6 automorphisms. Just put it in that normal form and then look at the permutations of the coordinates. Now, these permutations will certainly act on the flex points, so we just have to check the statement that if an automorphism fixes all 3 flex points, then it must be the identity. And I won't try to prove that, but it's not very difficult. Well, this statement that these elliptic curves always have 6 automorphisms may look a little mysterious, since if you start with a general one, it doesn't look as if it has any automorphisms. But that's the virtue of these projective simplifications of coordinates, that they can put any cubic curve and put it in a simple form. So here's an example. I'm just looking at the Hesse curve with k equals minus 2.4 as an example. We can take this with the same construction would work for any curve in Hesse normal form. We just put the flex points along the equator, thinking of the sphere as thinking of the projective plane as a sphere with opposite points identified. We put the flex points as evenly spaced points along the equator, point the center of symmetry at the North Pole, and then we'll get a figure like this, where the black curve represents the Hesse curve, and the red curves are the tangent lines at the 3 flex points. And in this picture, you can more or less see the symmetries. For example, if you just rotate the sphere 120 degrees around the North Pole, then this lobe of the sphere will map to this one. And if you rotate it 180 degrees around this point, then this lobe will go to this one. So you can more or less see the automorphisms with your bare eyes, and something similar would work for any curve in Hesse normal form. Or a way of doing this, which is less work to represent, is to take the plane and put the center of symmetry at the origin and put the flex points at infinity. If we do that, we'll get a slightly different picture. It looks like this. This is the same curve, but in this picture we see the North Pole in the old picture is now the center. The flex points are now points on the circle at infinity. And the tangent lines at the three flex points now represent asymptotic curves, asymptotic lines to the curve. So the curve gets closer and closer to the asymptotic line as it goes out to infinity in any direction. I can quickly show you all possible real cubic curves. This is the limiting case as k goes to minus infinity. For k going to minus infinity, the curve degenerates into a union of three straight lines. Then how k is increasing from minus infinity, so the lines remain straight, but the curve separates itself from them. And, well, this is very slow at the moment. It will speed up. So you see the triangle in the middle is getting smaller and smaller. This is for k less than minus 2. At minus 2, the curves cross each other. And at plus 1, a singularity suddenly appears in the middle. It's just the one singular point, k equals 1, that I mentioned before. And the limit as k goes to plus infinity, we're converging again to a union of three straight lines. So that's, in this picture, that's all possible real cubic curves. Well, so far I've been talking about cubic curves over the real numbers. The complex theory is much more standard and can be found in any textbook. But just to state very briefly what the basic facts are, any complex cubic curve is topologically a torus. It doesn't necessarily have this shape. There are many different possible shapes that a torus can have, but it's topologically this. And if we choose a base point, then there's the associated group, isomorphic. Well, the torus if we could just consider it as a topological group, there's a unique structure. It's just a direct sum of two circle groups. This is actually a Riemann surface, but I'm ignoring that for the moment. Well, if we take each circle group has 3 elements of order 2, so the direct sum has 9 elements of order 3. The sum has 9 elements of order 3. So every complex cubic curve has 9 flex points. And these form a marvelous property. Here you have 9 flex points. And if you take any 2 flex points, remember the theorem that the line joining any 2 flex points must intersect the curve in a third flex point. That's true also over the complex numbers. Now, you've got a diagram so that you have 9 points such that any 2 points determine a line, and you get 12 lines in this way, and any 2 of these lines intersect in a unique point. Now, you can't really draw this diagram in three-dimensional space. It's essentially a complex picture, but you can sort of represent it schematically as in this picture. If you think of the curve itself as being a topologically a torus, you can think of it as a square with opposite sides identified. And then the lines joining these points, of course, are not in the curve, so they're outside this torus, but you can draw them in this way. So, well, for example, if we take the line joining this point to this one, it hits this point, a line joining this point to this point hits this point. It's a little more obscure if you take the line, say, joining this point to this point. But remember, opposite sides are identified, so you follow this line and goes to point B, which goes on to point B here through this point, and to C, goes back to go through again. So this is a marvelous configuration which really exists only in complex space. It's usually called the Hesse configuration, but there's a remark in Ardebani and Dolgochev that this was already known to Maclaurin. I don't know. I haven't seen it in Maclaurin, so I don't know quite what he said. But it's an interesting remark. Oh, we can also look at the group of automorphisms of the complex case. In this case, I'll just go over it very rapidly. The symmetry group of automorphisms of a complex curve always has at least 18 elements. Well, there's an obvious element of order 2. For example, in the Hesse normal form, interchanging two coordinate axes, we get an element of order 2. But there's also a group of order 9 rather, which we can get by just using the group structure and looking at translations by flex points. So if we map P to P plus a flex point, we get an automorphism without any fixed points. And the theorem is that this automorphism of the elliptic curve extends uniquely to an automorphism of the whole projective space. So altogether we get at least 18 elements. And in special cases, there'll be extra elements. Some groups, if you take a square torus, then there's a 90-degree rotation. If you take a hexagonal torus, there's also a 60-degree rotation. So you get a slightly bigger group of automorphisms. Now the classical, if you look in any textbook, you'll see this kind of description of cubic curves. You in the affine case, and working in the plane, you set y square equal to a cubic polynomial in x. And you can always change coordinates to reduce this cubic polynomial to this kind, so they're just two complex coefficients. And the theorem is that this complex curve is always projectively equivalent to a curve in this normal form, every smooth complex curve. And the curve in this normal form is smooth if and only if this polynomial on the right has distinct roots, which reduces to this discriminant condition. And a complete invariant is given by this invariant, I think is actually up to is essentially the formula given by Felix Klein. So a curve is completely determined by this complex number up to a complex change of coordinates. And notice that the denominator vanishes only in the case of a singular curve. So whenever the curve is non-singular, this is a finite complex number. So the theory is very simple. I gave two names here now. The Weierstrass in the 19th century was using conformal isomorphism between curves. And the theorems, as far as conformal isomorphism is concerned, are due to Weierstrass. Nagel in the 20th century pointed out that you get the same result using projective equivalence. So there's two complex curves two complex elliptic curves are conformally isomorphic, then they're actually projectively equivalent. Well, so in complex case, we have a single number. In the real case, we have a single number. Oh, well, these are related to the symmetry. I mentioned that some curves have square symmetry or hexagonal symmetry. You can just read this off from this invariant J or from the coefficients A and B in an easy way. Well, now let's suppose we start with a curve in the Hesse normal form. So there's an invariant K, which in the complex case is a complex number, or in the real case is a real number. That we can consider that same curve over the complex numbers, and using Nagel's theorem, you can take the Hesse normal form and convert it to the classical normal form and compute J, and this is the graph you get, or the formula. The formula is true over the complex numbers. The graph only applies to the real numbers. So it's looks like a very messy curve, but you notice the curve has, the formula has degree, is a rational function of degree 12, so that if you're given a value of J, there are generically 12 different values of K. But in the real case, it's much simpler. Giving a value of J just means you're specifying a horizontal line. And you'll notice from the picture that every horizontal line intersects this curve in exactly 2 points. Well, it's visible. You can see it from the picture, or you can check it algebraically. You check it in detail. So now, remember the theorem I said was that K determines the class of the curve uniquely over the real numbers. So what we see from this picture is that for every complex curve with a real J invariant, there are exactly two real corresponding maps, and you can corresponding curves, and you can describe them in a very simple way. You just make a rotation of the coordinates, changing the sign of the x-coordinate and moving the y-coordinate by I over the complex numbers. That gives you a new curve which is equivalent to it. So it has the same J invariant. But over the real numbers, rotation by I is bad. So it gives you a very different curve. Here's just a typical example. Here are two curves, two real curves with the same value of K, but different values of J. And the secret is that over the complex plane, this polynomial defining them has a triangle of, has roots forming a triangle, and changing the sign of Z, the sign of X means we rotate this triangle 180 degrees. That doesn't make any difference in the complex case, but it leads to a very different real curve. Well, I seem to have used up my time, so maybe I should stop here.